that doesn't matter. So I hope you have seen that in the Wheeler. Have you seen have I uploaded the slides in the Wheeler or no?
Yes, I saw.
Yeah, okay.
Can you wait a few seconds? The recording is still waiting.
Okay, yeah.
Ma'am, it started.
Okay, started, right?
Yes, sir.
So we were doing the third postulate, and if you remember, we said that if I given an arbitrary wave function psi, if I make a measurement of A, in general, the values that will be returned will not be the same, but will be one of the eigenvalues of A. Okay, with some probability. So it's not definite, but there is a probability. And as I said, the probability can be predicted by expanding psi in terms of the eigenfunctions of A, which I call phi I. Then the probability of getting one of the eigenvalues, lambda I, is nothing but mod Ci square. So if you remember our definition, the operator A has eigenfunctions, which I am calling phi I, the eigenvalues, which I am calling lambda. So that is what it was. So this is the Copenhagen interpretation. And in that case, I use the average value, which is denoted in the following manner in the Dirac notation, but it is just an average value. And that would be obviously by the interpretation mod Ci square lambda. Okay, I equal to whatever. And we had a very important theorem that this expansion is exact provided this set is a complete set, and that's what it is. So we already proved that the Hermitian operator, not proved, sorry, I stated that the Hermitian operator eigenfunctions can be constructed to form a complete set of orthonormal bases. Very important thing here is orthonormal functions or orthonormal bases. This is very important. So when I've expanded their complete set and these phi i's are orthonormal, just remember this. Then I said that this average value, the way I have written the Copenhagen interpretation, you can see that the average value calculation requires the knowledge of these coefficients, requires the knowledge of the phi I, which can be obtained, of course, there's no problem. And eventually you can sum over, but it's a very complicated expression because you have to sum over so many states, right? This can actually be simplified. And the entire thing can be written only in terms of this and this. So which is my given conditions, the state of the system and the dynamical observable, that is sufficient to write the average value. Okay, so that is what I will show later. But what is important now is to first realize that an arbitrary state will give you the eigenvalues of A with some probability. So that is very, very important. That we will not get definite value. So that is not guaranteed, but in certain cases we'll get definite value, and those are the cases which we say stationary states of that operator. So we'll come to that. Let me now first tell you, so I'm starting today new topic now. How do I get these coefficients? Note that I have expanded psi in terms of the complete orthonormal set, and how do I get coefficient? I think I've done this before also. So the kth coefficient I wrote down is an integral between phi k and psi. So this is the Dirac notation. In the ordinary notation, it will be phi k star x, psi of x dx. And I showed why is it ck? You take the right hand side, expand the psi k in terms of phi k star x, phi I of x dx, and the coefficients. So in terms of your coefficients, ci phi I. If you expand these, then you can see, I think I have done that last time, and that is where we probably completed. Ci, this is a Kronecker delta, delta Ki. So when I'm summing over I must be equal to K. K is a specific function, I is a dummy index. So I must be equal to K. So the result of this is Ck. So that is how I prove. The Ck is 5K. Is it okay? So if there are any questions, please ask me. So I'm writing in Dirac notation, but you can write in simple notation.
Sir, could you repeat, please?
Sir, switching of integration and summation must be permitted, right?
What is switching up?
Integration and summation must be permitted, right?
Yeah, within the psi I have summed over Ci phi I. And Ci is a number which comes out. Yeah, it doesn't matter. I could have put this here. It has no meaning. It's the same.
No, sir, for infinite series, I mean, the order switching is not that, I mean, it's not
Yeah.
always guaranteed, right?
Well, I mean, what I'm trying to say that if you integrate term by term, that's what it means. It means here. That phi k star x, phi I x, I'm integrating term by term. Whatever numbers are there here. So I integrate and sum. And for each integral, I have to have a coefficient. So the problem is that if I put the integral here, the coefficient also must go inside. Okay. So the coefficient cannot be left outside the summation sign, right? Because this is sum over I. So it's the same thing here. Okay. So if it is so, then I come back to the probability. I come back to the
Sir?
probability. Yes.
So there will be sign where you written RH is equal to Ci pi
Yeah.
star k.
This is phi x I. What is the problem? So this is what I want to prove. I want to prove this.
Okay.
So this is what I want to prove. So I have taken the right hand side. Psi x I have expanded and I show that that is equal to Ck. Okay. So I have shown that each of the coefficient is nothing but integral of the corresponding eigenfunction with the psi. So given a psi and the eigenfunctions, I can get each Ci. So this expansion is known. Then what I am trying to tell that the probability I know is Ci square, which is equal to Ci star Ci. So if you look at this integral, the coefficient value Ci phi star psi, then I have it as at a Ci star Ci. So the average value would now be sum over probability times lambda. That's the average value. Now this probability lambda is nothing but Ci star. So I can write in the following manner: sum over I, Ci star R lambda I C. So I've just, these are all numbers, so I can scramble them any way I want, right? Okay. I would like to show that this quantity, whatever I have written here, is nothing but a very simple integral. Psi star x a psi x, which in Dirac notation can be written as psi a psi. So I want to show that the average value, which by Copenhagen interpretation is the probability times the lambda arithmetic summation, that can actually be written simply in terms of these, which is very, very simple because it just means I need to know the dynamical observable and the state of the system. I don't need to find out how that state of the system psi can be resolved in terms of the eigenfunction. So this equation I don't need. I don't need this entire thing. I don't need Ci, I don't need lambda I, but by the Copenhagen interpretation, this is the correct formula. What I am saying that this is identical to this. So this formula is identical to this, and that is what I will show now. Okay, so let me again start from the right hand side and show that this is equal to this. So basically I want to show these two terms identical. So the right hand side is sum over psi star. I'm writing in the full form, psi x dx. Now to show this, I will expand because obviously unless I expand, I cannot show this because this requires Ci and lambda. So I will expand each of these by Ci star phi I. So this becomes sum over I. For this, I will bring in another dummy index, let's say sum over j, and this will become Cj. Then I have an integral over phi I star x, a phi j of x dx. I want to repeat this part very carefully. What I have done is that I have taken this quantity and I am expanding this. So when I expand psi star x, I am taking a dummy index I, which is Ci star phi I star x, because it's a complex conjugate. For the right hand side, I am expanding with j, Cj phi jx. Then I have to integrate. What are within the integrations? Ci star Cj are definitely not within the integration. So I take them out. What is integration is phi I star x, a phi j of x. So I only integrate this. Please let me know if this is clear. So this is very simple linear algebra. You just have to keep dummy. Remember, I require two different dummy indices. One for psi star, one for psi. That's key thing. Then let me analyze this term. Sum over I, sum over j, Ci star Cj. Now when I analyze, you know that these are eigenfunctions of the operator A. So A phi j is going to become lambda j phi j, right? So I can take out lambda j outside. And this will now become phi I star x phi j of x dx. Right? So I put a lambda phi j is lambda j phi j. Integration is now only over phi I star phi j. And now we know this is Schrodinger delta. These are the orthonormal eigenfunctions. So I have a result which is very simple. Sum over ij, Ci star Cj, lambda j, delta ij. Because of the delta ij, double summation actually vanishes. So let's say j must be equal to I, or I must be equal to j. One of them will be there, and in which case the result will become sum over I. Let's say j is equal to I. So wherever there is a j, I put I, Ci star Ci. This becomes lambda I, and this is just 1. And now you see, my average value, which by Copenhagen interpretation was mod Ci square lambda I, which is nothing but Ci star lambda I Ci. And that is nothing but psi star a psi. This is Ci star lambda I Ci. I can scramble them. So I can then say that the average value, which was nothing but, this is the Copenhagen interpretation, where it appeared that I required the coefficient and the eigenvalues, can now be written as integral psi a psi which is a much simpler thing because I don't need anything. But remember, this is very, very important because otherwise I could not have defined the average value because I needed to know how do I take the average because I get only eigenvalues. Remember, the experiment gives you only eigenvalues. So of course I have to take our average of eigenvalues. How do I take average? That is where the probability comes. How do I get the mod Ci square? By expansion of this. That's the interpretation. So it appeared that I require all this expansion, complication, how to get my initial state into a combination of eigenstates. What are the eigenvalues of the operator A? So I define it in this manner, but then I show there is a simpler formula, which is just this, which is basically nothing but this complicated thing, sum over Ci star Ci lambda. And I can then write finally the average value is integral psi star a psi dx.
So the entire postulate is that Ci square, mod Ci square is the probability of measuring lambda I.
Right.
That is the
Right. That is the key
entire
thing.
postulate.
That's the key thing. The rest is mathematics. You're right. The rest is mathematics. And I'm saying that since there's only a probabilistic description, you can only get an average value. And then I showed by this mathematics that the average value actually could be obtained straight away from psi and A. I didn't need all this. These are only needed for interpretation. Of course, if it is not there, I don't know what is the average value. I would not have been able to do this. Having known this, I can write this formulae simply in terms of this, and this is much simpler because I actually don't need to know the eigenvalues of the A. I don't need to know how psi is expanded in terms of phi i's. It is simple integral of psi star A. So the psi is already given to you, the operator is already given to you, the first postulate provides you psi, the second postulate provides you A, and then I say the average value is just this. If you simply say what is a measurement, measurement has a probabilistic interpretation, so I don't care, that's the average value is the best way to report the measurement, and that's it. Actually, the entire postulate tree I can cut down. Many textbooks just write this. That in quantum mechanics, the measurements are not definite, so the only thing that we can describe is an average value, and this is how the average value is written. I mean, I could have simplified the whole thing. But then it doesn't tell you how did you get this. Now I have explained to everything that the way I get this is that this probability is first measured in terms of this coefficient. The coefficient which accompanies the expansion of psi into a particular eigenfunction. And that is very intuitive because we get only eigenvalues. So what I'm saying, it is very intuitive to think that the probability of getting an eigenvalue lambda I is actually the corresponding Ci, corresponding to the eigenfunction phi I. Phi I is an eigenfunction of the operator A, right? With the eigenvalue lambda I. So that's the important expression. So please note this expression here and this expression here. Okay, so I know the lambda I. This is a coefficient corresponding to the eigenfunction for lambda I. And that is the probability of getting lambda. So if you look at these three things, it actually tells you everything. And that's the Copenhagen interpretation, which is very intuitive. The rest, then I say, okay, that's a probability, this must be average, and the rest is mathematics to show that since these are complete orthonormal set, I can do all kinds of things. I first calculated CK, then I showed this quantity. So that's very easy. Actually, the CKs are not required. Yes.
Sir, also I had another question that the fact that you said that the result of any measurement, I mean the first measurement, not successive, the first measurement will be one of the eigenvalues. This you said. I just wanted to ask that, is that a fact just from, I mean, we have already decided our operators based on other aspects, and we are seeing from experiments we have seen that we are only getting the eigenvalues.
Yes.
Or is it the other way around, that we have made operators to give us eigenvalues?
Okay, I mean both. See, I mean, how are the operators formed? Because of experiment, right? So it's not that the operator came first. It's a whole apparatus is built together.
Okay.
All right. What I wanted to tell you, very interestingly, when I proved this, I simply expanded psi and I could prove this. I did not need this particular expression that I showed you, that the CK, how do you get the CK? I didn't need this actually. Okay? But it's important that I could have proved the other way around. This proof, this mathematical proof, I said psi is so. What I have proved here, let me again tell you. I am proving here as psi A side from this side, which is equal to sum over I mod Ci square lambda. This is what I proved. By simply expanding psi in terms of Ci and using operator acting on the eigenfunctions to give you lambda times eigenfunction. I didn't need actually the expression of Ci. That means I did not need the fact that Ci is phi k star at psi. I didn't need this. If you see very carefully. On the other hand, I can prove from this side to this side. which means I can start from Ci square lambda I and show that this is equal to psi Si. Probably you will argue that would have been better because you have already explained that the average value is nothing but Ci star Ci lambda I, and now show from here that it is equal to psi star Si. I actually made a statement and showed this simply because this is little bit more complicated, and to show this I would have actually required this expression of Ci star and Ci and an expression of identity, which I will not do right now, but I will show it a little bit later when you are more confident of the Dirac notation. Dirac notation is very easy. So remember, this is what I could have shown, but what I did actually was to show this. This is what I did. I first started with this, showed this is equal to this, and hence I said it is equal to average. I hope it is clear, but you can always say, can you show this to this? Is it both ways derivable? Yes, the answer is yes. I don't want to do right now, but we can do it. And then I would actually require this expression of the coefficient that Ck is phi k psi. This expression will be required. Okay, this is what is going to be required. All right, but whatever it is, finally what I'm saying that this entire thing is very simple. There is a indeterminism in getting the values, and hence I can get an average value which is nothing but psi star Si. Whichever way I do it, these all are same. Okay, but this is more complex. This is very simple. Because I have given psi, I have given a, simply integrate. Is it clear? The question that somebody asked, what happens in the second measurement, I think I will discuss a little bit later. It's very difficult, and Dirac actually, in Dirac's textbook, it's actually discussed very nicely, but I will pend it for the time being. I want to go to the postulate 4, which is basically a condition. I wouldn't even call it a postulate, it's actually a condition. The condition is the following, that suppose the given wave function psi or the given state is an eigenfunction of the operator A. Okay, suppose this is an eigenfunction of the operator. Then what will happen is that the original postulate that you will get one of the eigenvalues is still true, but now you will actually get an eigenvalue which is a definite eigenvalue, only one eigenvalue. So suppose psi is phi I. I've used 3 equalities, means psi is defined to be phi I. Then what will happen is that the result of the measurement will give you a definite value, and that is lambda I, the corresponding eigenfunction. Remember the eigenvalue equation, A phi I equal to lambda I phi I. So psi is phi I will only get a definite value lambda I. So obviously it does not contradict this postulate, because here I said you will only get eigenvalues of A, but I said with some probability. Here also it is some probability. The probability is that the lambda I is 1. The probability of getting lambda I is 1. Normalized probability. Probability of getting lambda j is 0, where j is not equal to I. I hope it's clear. So any other eigenvalue, the probability is nil. So it's also a probability mathematically. So, but it's now definite. At this actually, creates a lot of interest, and that these are the states where the value is definite. So just like classical mechanics. Of course, in that case, Ci equal to 1, all Cj is 0, J not equal to. I hope it's clear. Since the probability is 1, and that is because Ci equal to 1. Why is Ci equal to 1? Because psi is equal to phi I. So when I expand these in terms of some Cj phi j, dummy variable, so since psi is only phi I, so rest of them don't appear. So only when j equal to I, it survives, rest is 0. Which can also be written from phi k psi. So if you do phi k psi, remember my ck is nothing but phi k psi, and now psi is phi I, so it is phi k phi I. So you can see is delta ki. So only when k equal to I, there's a coefficient, otherwise it is 0. So either way, there are many ways you can answer this question. So what I'm trying to say, if psi is a definite eigenfunction, then if I expand this psi in terms of a linear combination of phi's, only this ith coefficient is 1, the rest of the coefficient is 0. And that can be shown from here also. Because this is my definition, remember, of ck, which I have found from the orthonormality. So basically there is only one function. And hence I get lambda I probability also is 1. So I get everything definite. So that's really, it's quite beautiful. I have to write beautiful here. It's beautiful because I'm able to get classical like situation. But this is only when psi is equal to phi I. One of the eigenstates of the operator. Such a state is called, quote unquote, stationary state. This is just a definition. Stationary state of the operator A. Now you know why they are called stationary state, because these are states where the values are not changing. You can do the same thought experiment, identical system, everybody gets the same value. So it's really interesting. And I just get a stationary state. Of course, for every operator, and that is important to note, for every operator, there are different stationary states. Because those stationary states are now the eigenstates of the operator A. Because remember, our starting point itself, that suppose psi is an eigenfunction of the operator. So they are all eigenstates of the operator. So every operator has its own eigenfunction. So stationary states are also different. There is nothing called unique stationary state. So the one important stationary state that we will discuss is the stationary state of Hamiltonian. And I repeat this, that's important only because the Hamiltonian is, the energy is very, very important. And that is because of the thermodynamics. So those stationary states, I can write now as H phi I equal to Ei phi I. So H is the Hamiltonian, which is the energy operator. Phi I is the eigenfunction, these are the eigenvalues. And these states happen to be very, very important because these are stationary states of energy. Just 1 minute, please. Hello. আমি জানি সেটা আপনি চেঞ্জ করুন। হ্যাঁ জানি আমি, দেখুন আপনি দেখুন কি করতে পারেন। ফের আমি আপনার আমাদের ক্লাসে আছি। হ্যাঁ আমি এখন একটা ক্লাসে আছি আসলে। I'm sorry. Yeah. I'm sorry. So the important things are the stationary states of energy, which can be written as the Hamiltonian acting on eigenstates phi I, energy times phi I. So this is very often, we don't call it phi, we just call it psi. You must have heard this H psi equal to E psi as a logo of quantum mechanics many times. Okay, except that I'm calling it phi. That's the symbol. So this is very often very interest in chemistry. So chemistry has a lot of interest of finding stationary states. and I should say stationary states of energy. This is my primary interest in chemistry. So many of the applications which will come after the postulates are over are actually to find out IISER equal to ESI. However, interestingly, IISER equal to ESI is satisfied only for a class of methods where the states, initial states, are eigenfunctions of the energy operator. So this is not, in a way, this is not a postulate that every psi will satisfy IISER equal to ESI. So that is the reason I said this postulate is a condition. This is a condition of a stationary state that those psi's which satisfy these have this interpretation that their values are stationary, that the values are identical, energy is stationary. We will get several meaning of the stationary probably in the next class when I will do the Ehrenfest theorem. We will get several meaning of the stationarity, but at this point, they are called stationary states of energy. Unfortunately, when I get stationary state of energy, it's only energy which is stationary. If I want to now measure another operator, then this psi may not be an eigenfunction of that operator. Then, of course, I have to go back to postulate 3 for that operator. I hope you are understanding. So let's say I have this is psi is an eigenfunction of the Hamiltonian, but I have another operator, let's say dipole moment or angular momentum. I'm just giving an example for which this psi is not an eigenfunction. Then if I make a measurement of angular momentum or that operator, I will only get a scatter of values just like the postulate 3 stated, because that particular state is not an eigenfunction of that operator. Is it clear? So if you have any question here, please ask me. So for any other operator, this may not be true. However, what is of interest to ask, and this is a great interest. Let's say I have a function which is already a stationary state of IISER. Then stationary state of energy. Then I want to ask the question, under what conditions will this psi be a stationary state of another operator? I hope you understand my question. Is it a hopeless case that it is only for energy, or is it possible that this state can also be an eigenfunction of another operator, and hence it's a stationary state of another operator? The answer is yes. Hence, I'm asking the question, under what condition it is true? And these conditions are very, very important in quantum mechanics. And the condition is actually stated by a theorem, a very general theorem, which I will again not prove for the time being at least, because that will slow down. But those can be proved either in the tutorial or some succeeding tutorial will prove. So the theorem is the following. If two operators, of course we are specifically interested in Hermitian operator, but theorem is more general. If two operators commute, they have simultaneous or common eigenfunctions, or at least eigenfunctions can be constructed such that they are common. Now, this is a little complicated statement. When you prove, you realize why I'm saying can be constructed. But the point that I'm trying to say, two operators commute, they have simultaneous eigenfunctions, which means, in a very simple way, if A commutes with B, another operator, I hope all of you know what is a commutator. It means that the AB is equal to BA. If I subtract AB with BA, it is 0. So AB and BA are identical. Normally, it is not, right? So the two operators commute. So this is basically nothing but AB minus BA, commutation. Then they have simultaneous eigenfunctions. So I can write in the following manner: A phi I equal to AI phi I, B also has the same eigenfunction, B phi I equal to Bi phi I. Note, however, the eigenvalues can be different. The theorem only talks about eigenfunctions. Okay? So this is the theorem that if two, mathematically, if two operators commute, they have simultaneous eigenfunction. And the point is that the theorem is also reverse. That means if they have simultaneous eigenfunctions, one can prove that they commute. So one can also show that if A and B have common eigenfunctions, they commute. It will really be very useful to prove this at some point of time. But at this point, I wanted to finish the postulate, so I will not worry about it. Which means I now have a clue to the question that while this is stationary to the Hamiltonian, I can also have operators for which this will be stationary. What are those operators? Those are the operators, AI, let's say, which commute with the Hamiltonian. Is it clear? So for these operators, the same eigenfunction of the Hamiltonian will also be an eigenfunction of this operator. In case I can find operators which commute to the Hamiltonian. So there's a lot of interest in physics to find out the commuting operators with Hamiltonian. For a completely different reasons, they will be called constants of motion. When you read physics, you will realize, and you will realize this also on Tuesday, when I actually derive the Ehrenfest theorem. These are actually called constants of motion, all operators which commute to the Hamiltonian. So I should say, in a very simple way, the simplicity of physics is to actually search for constants of motion. Somebody told me that the whole of physics is nothing but searching constants of motion. A very simplification of the physics, of course. But you search for constants of motion, operators which come into the Hamiltonian. Then I am very, very happy because not only one energy, but all other states will also become stationary. Such beautiful. So that beautiful that I wrote will now extend to many, many variables, many, many observables. So I think this is a very interesting idea. And this is the idea that based on which group theory is made. Many of you have heard group theory in quantum mechanics. Group theory is actually searching for those operators. And very often those operators, the operators AIs, which commute with Hamiltonian, are called symmetry operators. So you can see why group theory deals with symmetry. So these are basically the symmetry. So the symmetry of a system is determined by operators which commute to the Hamiltonian in a very simple way. And group theory deals with combination of such operators. We will not bother about it at this point when the group theory will be separately taught as a subject. But what I'm trying to say that the idea of a definite value can be extended between mutually commuting operators. Mutually commuting operators. So I can have a mutually commuting operators. A, B, C. Mutually commuting. Which means A commutes with B, this is the commutator with B, B commutes with C, C commutes with A. All of them also. This is called mutually commuting. Means if I have three operators, each of them has to commute with the other. If only these two commute, you cannot say that C commutes with A. I hope it's very clear. There are so many examples. That A commutes with B, B commutes with C, but doesn't mean that the C commutes with A. But So if I want three operators, let's say Hamiltonian, A and B, to have simultaneous eigenfunctions, all three must commute. There must be a mutually commuting set. Then I can say that the eigenfunctions of the Hamiltonian are also eigenfunctions of A and B, and I can have, in the stationary state of energy, they will also be stationary. Of course, their values will be different. Remember the theorem. The eigenfunction is same, not the eigenvalues. And of course, that is understandable. The same state can be an eigenfunction of two operators, but their values cannot be same because they are all different things. Energy, momentum, how can the values be same? The state, but the same state, I don't get a scatter. So you can imagine if you can find many such mutually commuting operators and trap your state of the system into one of the eigenstates of these operators, it's so beautiful. Right? You get 3, you can have 4, 5, 6. More and more number you get, it means more symmetry the system has. So when you will understand, when you will go to group theory, you will understand the very symmetric system.
Sir,
Yes.
in I mean, assuming we are still in classical mechanics, we have that formula for position. For energy, right? Kinetic energy and potential energy, and those add up to give us the total energy of the particle. So I just wanted to ask that I mean, you said the main aim was to find commutating operators with the Hamiltonian so that we can have the same energy, same eigenstate to
Right.
give us the eigenvalues of different operators. So, sir, if we have instead of the Hamiltonian, if we have the momentum operator, so cannot we just back calculate the energy from the commutating operators of the momentum operator? Will it not be possible?
No. That's not possible. You can find out only kinetic energy. If a state is an eigenfunction of px, it will be also an eigenfunction of px square. Please note, if a phi I equal to lambda phi I, then a square is an operator for which also phi I is an eigenfunction, with lambda I square as the number. It's very easy to show, right? You just apply a twice. Yeah. So of course, if you have eigenfunction of p, you know px squared by 2n. That is easy, but not the total energy, because total energy has potential energy, right?
Okay, so because I thought while writing down the Schrodinger equation, we have already written v as a function of x. So don't we know?
Yes,
don't we already know v as a function of x?
Yeah, v is a function of x, but the eigenfunction of px is not the eigenfunction of v of x.
Oh, okay. Now,
See, so these are some of the two operators. So how can the same eigenfunction be the eigenfunction of Hamiltonian unless it's also an eigenfunction of v of x? The problem is px does not commute with x. And that is the heart of the uncertainty principle, that the x and px are not the commuting operators. In fact, if Professor Sen is there, I will request her to do this in the tutorial. I don't know if he's there, but I will tell her if she's not there. What is the result of this commutation? In fact, the result is h cross over I. Because px is h over I ddx. So xpx commutation is very important. Okay, so you will do this exercise. It's actually called in the IH cross or whatever. The negative of this is normally written. So it's important to understand that they don't commute. Because they don't commute, you can never have simultaneous eigenfunction of px and x. Now you know why uncertainty principle. If you want, in fact, one of them becomes, other one becomes completely crazy. So of course, you can do this very easily by taking any function, px xi. That is nothing but h cross over I ddx of xi minus xpxi. So please do this. So it is minus h cross over I x ddxi. So d psi dx. So you can see here they are not identical because you differentiate x d psi dx but also psi 1. So eventually the result will become h cross over I psi. This is my commutator. So the commutator of px of x is equal to h cross over I. Is it right? For any psi. I will ask that to be done in the tutorial once more. So they don't commute. So that's the problem. The kinetic energy does not commute with potential energy. This is a very big problem. If the potential is 0, then you are right. Because now this does not exist. Then Hamiltonian commutes with the kinetic energy. Is it clear?
Okay, sir.
Yeah. Any other question? Although we are coming to the end of the class, I will finish with the postulate because I have only one final postulate. Many times the postulate 3 I break up into postulate 3 and 4. This is postulate 5. 3 and 4 I break up in the following manner. One is the interpretation. I stop here. Another is the average value. So the postulate 4 is often the average value. This becomes postulate 5, but it doesn't matter what you number. Okay, please don't worry. So in my new numbering system, I will now call this postulate 5 and I will end with this. This is the final postulate of quantum mechanics. Now it says for any arbitrary psi, and that is important, that's when it becomes postulate. For any arbitrary psi, the following equation, which is known as the time dependent Schrodinger equation, holds. And I will just write this. H acting on psi, this is any arbitrary psi, equal to IH cross del psi del. Note that for the first time, I brought in the concept of time. So far, time was not an issue. This is the only postulate through which time will come. And I will show that for all of quantum chemistry, actually the time is irrelevant. And this can be shown by what I'm going to do next time. So next time I'm going to discuss the time and then you'll see that we can forget about the time. Now note this postulate. It means that the operator acting on psi. So psi is now a time dependent operator function, x and t. It is also time. The operator acting on psi is equal to is cross the first derivative of psi with time. So the change of psi with time is governed by the action of the Hamiltonian on psi. First derivative. That is the meaning of this postulate. This is called the time-dependent Schrodinger equation. What we wrote before was a condition, H psi equal to E psi. This is a condition. This is not a postulate in that sense because it is not true for any psi. But this is true for arbitrary psi. Also, it is true for this kind of psi. This is also often called the Schrodinger equation. And very often that is a confusion. So I would rather say this is called time-independent Schrodinger equation. But the time-independent Schrodinger equation is only a condition of stationarity. So this is a condition of stationarity, of energy, and it could be other operators provided those operators commute with Hamiltonian, as I explained to you just now. So please remember, both are called Schrodinger equation, and you have to understand that this is really my Schrodinger equation. This is not a postulate. This is a condition of stationarity, which I explained in the postulate. I'm going to come back to the postulate 5, explain the time, and that is the final thing. So I will be able to finish on Tuesday. I think so that Thursday we can comfortably have the quiz. And if anything is left out as a tutorial, I'll do on Thursday itself after the quiz. So that the time part is a corollary of the postulate, and that is called the Ehrenfest theorem. I've been talking about it. Ehrenfest is a very famous scientist, and I will actually explain that theorem, for to explain this time part and explain the Ehrenfest theorem on the next class. Okay? So today it is already 6 o'clock. It's heading to 6 o'clock, so I will stop. Are there any questions? several such commutators you should do on your own.
Sir, can you
Yeah.
please go to the part of the note where the average value problem was discussed?
Yes. So that was the last postulate, postulate 3. Yes.
Sir, just a question. Here, the CIs are actually the coefficients of the eigenstates. Am I right?
Coefficients of expanding. 1 minute. Let us talk very accurately. Otherwise, there will be coefficients of expanding psi in terms of the eigenstates of A. This is CI.
Okay, sir. Okay.
Because
No.
psi is a linear combination of complete set. This is a complete orthonormal set. I have already proved that the Hermitian operator has complete orthonormal sets. Okay? So in terms of that, unfortunately, I have not proved every theorem. I have stated that's one theorem I have not proved. Today I stated the commuting theorem, which I did not prove. And those proofs are useless, but useful. Sorry, those proofs are useful, but I didn't want to hold out the postulates. They can be offline discussed. They can be discussed in a tutorial, a separate class. That is what I will try to do on Thursday. After I finish the Ehrenfest theorem, on Tuesday, 9 to 10, Professor Sangita Sen will take the class. 10 to 11, I will take the class. And Thursday, there will be quiz. I hope you remember. And after the quiz, I will discuss the whatever is left out, some of the theorems that I will hold. And then we will move to the application of the Schrodinger equation, time-independent Schrodinger equation. So application of the stationarity for different Hamiltonians. Okay. So basically, we will do this application of this equation to different problems, and one of the famous problems are particle in a box. A free particle and particle in a box is very important to understand. I think Professor Sen will take over again at that point, which will be basically week after, not next week after. Okay, so I think it's very clear now. The Thursday we'll have the quiz, and the quiz will contain almost everything, at least up to today. Ehrenfest theorem is really, something that will not come in the quiz, but at least up to today, the quiz will come in the Thursday's class at 5 p.m. And quiz will probably be half an hour maximum. So after that, I will take the rest of the 30 minutes to complete what is not there. Okay, and of course Tuesday I'm taking the class. Yeah? Tuesday at 10 o'clock I'll take, but then Professor Sen will take at 9 o'clock. So you should be on time. Okay, so let me stop and come back to the screen. Yeah. So is there any questions? Anybody has question? Please read the postulates. Go through once, twice, thrice. It's very important because this is all new. So we can discuss, as I said, we'll also, I have not decided whether it will be MOQ, Tiasha, MOQ or written. I have to talk to Professor Sangita Sen. MCQ, you mean not MOQ, MCQ or written, I don't know. I think MCQ is probably easier for, I don't know whom, easier for us or easier for you. What would you prefer? Tell me. Tiasha, you tell me, what do you prefer?
Hello, sir. Sir, if
Tisha, okay, sorry, not Tiasha.
yes, sir, Tisha.
Yeah,
Yes.
Today I sent you a mail.
Yes, sir. Yes, sir.
Yeah.
Sir, anything is fine for me. Like 30 minutes. Like if the questions are solvable within the time and we can upload the PDF, then it is fine. Otherwise, MCQ is also fine.
Okay,
So whatever
fine.
you all say.
So I have to discuss with Professor Sen, and we have not discussed that. So that's okay. Okay, all right. Yeah, thank you. Any other question? Otherwise, they'll leave today. We'll leave you for the next class. And please come back on Tuesday, 9 o'clock. Okay. Thank you. Thank you.